All right, so what I want to do here is just give a quick example of how to do calculations with both power and efficiency. Sorry for the quality of this video. I just had to scan the pictures quickly and just talk over it. So we're going to do a few questions with power and a few questions with efficiency. And then down here you're going to see, here's your questions that you're going to work on in class today on top of that. So the power example, so the first one is calculate the work a crane does to move a mass from 2,500 kilograms and lifting it from 2 meters to 25 meters. So H1 is 2 meters, H2 is 25 meters, the mass is 2,500 kilograms, and we want to find the work done. So work is the change in gravitational energy, so it's delta E. In this case, it's gravitational energy, so it's delta EG. And that's just the transfer of energy. So that was earlier derived as mg delta H. So we got mg, and then the delta H was 23 meters because it was lifted from 2 meters to 25 meters. So 25 minus 2 is 23. And that gives us 563,500 joules. So that's the amount of work done to lift that mass up that high. The amount of power is basically we take the work that we had here, 563,500. So power is delta EG, so it's the change in energy or the work done divided by time. So it's how quickly the work is done. So it's mg delta H over delta T. Plug in the value we got before, and we find that that gives us 37,567 watts. Now remember, a watt is a joule per second, the amount of energy dissipated per second. The energy per second, joules per second. That's a watt. Now since there's 1,000, this is 37,000 watts, we can say that that's approximately 38 kilowatts, or 1,000 watts. All right, the second one, we're accelerating a car, a 1,500 kilogram car from 5 meters per second to 20 meters per second. It takes 6 seconds. So power is the change in energy or the work done, and this case is delta EK per unit time. So what is delta EK? Well, it's the final kinetic energy minus the initial kinetic energy. Since it wasn't starting at rest, V1 is not 0, so we can't just ignore this term. So I plug in my values, and we get the amount of work done was 281,250 joules, and that's done in 6 seconds. So that gives us about 46,875 joules per second. And here I wrote joules per second is clearly a watt. And since this is a thousands, so you can have things like megawatts too. If there were three more zeros after this, we could have megawatts. This is a kilowatt, so this is 47 kilowatts. All right, for efficiency. Efficiency is the amount of useful output energy over how much is input. The output is always going to be smaller than the input. If you do your calculation and it's vice versa, switch it. That's all you have to do, because you've just mistaken which one was the output and which one was the input. Times 100%. So this gets actually pretty complicated. So the only hard part here is just deciding what's the output, what's the input, and that's the big struggle for these types of problems. So the first one says a washing machine is 30% efficient. That means that everything you input, you're only going to get 30% of it out. Okay. So 2,000 joules of electrical energy are input into the machine. Calculate the amount of useful output if it's only 30% efficient. And again, the number on top will be smaller than the number on the bottom. So what this says is, like, you literally, if you plug this in the wall, it's going to drain 2,000 joules of energy. But the amount of actual output that you get in terms of the spinning power and all that kind of stuff is only 30% of that. So it's going to be smaller. So here we have efficiency, 30%, input, 2,000 joules, output, unknown. Percent efficiency is E out over E in times 100%. Now, the percent efficiency was 30%, and that's 100%, so 30 divided by 100 is 0.3. So we can actually just get rid of that 100% by writing here, instead of 30%, write 0.3. If you wanted to leave it as 30 and leave the 100 over here, it'll come out the same at the end when you rearrange the formula. So that just becomes 0.3 times 2,000, so 600 joules, which makes sense. There's 600 joules actually output, and there was 2,000 input, which is only 30% efficiency. In the second one, what we have is calculate the efficiency of crane. So this crane is actually going to use 5.1 times 10 to the 5 joules of energy to lift 1,000 kilograms up 32 meters. It doesn't matter if it went from 0 to 32, 32 to 64. It doesn't matter as long as the difference is 32 meters and the acceleration of gravity is 9.8. So you see here, we've got the mass, your delta H, the E in. So you can see I messed it up. I actually wrote out in the first place. The E in is 5.1 times 10 to the 5 joules, or 510,000 joules. The output is unknown, the efficiency unknown. So what we do is we start with our equation and we say, well, that's the equation, but I don't know the output. So we calculate how much work is actually done to lift an object from any height 32 meters in distance. So 1,000 times 9.8 times 32 is 313,600 joules. So that's if you actually went out and you were 100% efficient at lifting an object 32 meters that was 1,000 kilograms, right? If you knew that for sure, that you were 100% efficient, it would only take you 313,600 joules. That's why it's the output, because that's how much it should actually take. That's how much you're actually doing. That's all you're getting out of this whole entire thing, is that's the output, is 313,600. And we know that it actually, we had to input 510,000 joules. So we had to input more. And the reason is that there's energy loss, it takes heat, there's noise, there's sound, there's friction in all the parts of the machine and all this kind of stuff that drains or loses, it's where the energy is lost to, remember the air quotes there. So when we divide those two numbers and multiply by 100%, we get that it's about 61% efficient. So it should have only taken 313,600 joules, but it actually took 510,000 joules, which was actually what was input, and therefore it was 61%. If we had input 313,600, we would get 100% efficiency. So you kind of have to talk it through like that when you're thinking about these problems. This next one, the power rating of an electrical device says that it's running at 900 watts of power. So we actually read on the back, it says 900 watts. This thing will take 900 watts or use 900 watts. If the device is run for 10 minutes and outputs 4.8 times 10 to the 5 joules of energy, calculate the efficiency. All right, 900 watts. The time is 10 minutes, which is 600 seconds. The output is 4.8 times 10 to the 5 joules, which is 480,000 joules. So I write this equation. Power is delta E over delta T. Delta E equals P times delta T. And so basically I took the power, which is 900, times it by 600. I got 540,000 joules. Now clearly we know this is the input, because this is literally, if this rating on the machine was 900 watts and we had it on for 600 seconds, this is how much would have to be input into that machine. Now here's the problem. What actually was given out from this machine was only 480,000. So it's less. And when we divide it, we get that it's an 89% efficient machine. So let's say this was a kettle and it was 900 watts. And it says on the back of the kettle, well, this is a 900 watt kettle. And we put it on for 10 minutes. We know that the amount of energy that would have been input into it would be 540,000 joules from the electrical outlet. But if we look at how much the water heated up inside the kettle, we may find that it was only 480,000 joules of energy actually gained to it. Okay? At this point, we know that that means that we're only at 89% efficiency. Okay? That's it. Good luck with the rest of the stuff.